Thank you very much. Thank you to the organizers. And it's really a great pleasure to be here and to speak. And I want to revisit some old questions about Torelli theorems that Arthur, of course, have very influential papers, especially with the supersingular K3s. And I want to try to sort of rethink a little bit how we might phrase Torelli theorems in positive characteristics. So I'll talk about joint work with Max Lieblich, who came up in the previous talk. And just to get ideas fixed, let me begin by reviewing some basic Torelli theorems over the complex numbers. And I'll say, I have in mind other Torelli theorems, but let me talk about K3 surfaces for this lecture. But so let's say we have a K3 surface. And so, well, what do you consider? You first consider the lattice, which is the singular cohomology with z coefficients, which has an inner product. And so there's sort of two bits of data. There's this, which is sort of the analytic part, and then there's the Hodge filtration. Which is somehow the algebraic part. So for the K3, of course, it just looks well, there's really just one piece. So really you just need to know this, which is the H0 of x kx. From that and the inner product, you can get the F1. And so the Torelli theorem, in its standard formulation, says the following. So two K3 surfaces x and y are isomorphic if and only if there exists an isomorphism lambda x, so that means including the inner product, preserving the filtrations.
But it doesn't mean that you can lift the isomorphism.
No. So this is a delicate question. So as people were I think so as Ofer says, so let me remark. And this is actually, I'm glad you asked, because I want to discuss this point in positive characteristics. So if, in general, you needed to take a Kähler class to a Kähler class. So so let me give it a name. Let's say sigma. If sigma takes a Kähler class to a Kähler class, then sigma lifts to an isomorphism let me put it sigma tilde x to y. Right. This is what you were asking, I think.
Yeah. And also it is unique, the lifting.
If it's unique. Let me not say anything on the spot. I'm not sure on my feet.
Well, more precisely, supposing you consider harm of x to y goes to harm of lambda x lambda y, what do you say about the that sense? Or isom of x to y.
Yeah. That's the question, right? Is it injective, right? Yeah.
It's injective.
No, that's the question.
Oh, okay.
Yeah, let maybe not say something wrong. So okay, yeah. Okay, and so right, and so in general, you can arrange this can arrange this by reflecting across -2 curves. So this is somehow a very classical story. And so, I mean, you see in the very formulation, it's not clear what you should do in positive characteristic because of this integral lattice, right? So, of course, Ogus proved a Torelli theorem for supersingular K3s. Which is really the only result I know which uses cohomology as sort of the, you have if you have an isomorphism of cohomology respecting some structure, then you have isomorphic varieties. Okay, so sort of the rough idea.
So when you say can arrange this, I think you also need maybe to apply -1, or not. I'm not sure, because the reflection along -2 curves cannot be enough if there are no -2. So you can have the automorphism -1, minus the identity,
Yeah.
certainly.
Yes.
And -1. This probably is.
Let's see. Yes, I'm sure you're right. Let me. So yeah, let me put a. You just put -1. Let me just put it like that. Okay, so the rough idea here is to try to make a formulation even in positive characteristic. We'll replace lambda x here by the derived category of coherent sheaves on X. And the Hodge filtration will get replaced by, so what filtration can you put on something coming out of the derived category? Well, you can go to the Grothendieck group, tensor Q, which by Riemann-Roch is the Chow group tensor Q. And there you have a filtration, which is filtration, I mean, it's graded, so gets replaced by the codimension filtration here. Now, this is a very loose sort of analogy, but I'll explain a Torelli theorem for K3s in this context and deduce consequences. Okay, so, but in general, I don't know to what extent. I mean, it could be that this is a much stronger kind of result or condition that you could have Torelli theorems sort of in the derived sense when it might not hold there. So.
So will the result you're trying to explain give a new proof of the complex numbers?
No. In fact, this is, I'll sketch the argument for the proof, which will reduce to the complex case, unfortunately. Yeah. All right, so let me give a precise statement. Okay, so K, let's say, is algebraically closed and characteristic not 2 for some technical reasons. And so X over K is a K3 surface. And so there's some of this came up in the previous talk, but let me get it on the board. So x and y are called Fourier-Mukai partners. If we have an equivalence of triangulated categories between the bounded derived categories of coherent sheaves. And as I said, so there's one point which I'll come back to later, but if you take the Grothendieck group of the triangulated category, you have to choose this isomorphism in the right way, but you have an isomorphism here with Chow groups. And actually for the theorems I'm going to discuss, I could pass to numerical equivalence, but anyway, that's not too important. So I view this as being filtered. And so this would be F2, F1, F0. Okay. So just in the simple way. And then the theorem is that if x and y are K3 surfaces, over K, and there exists an equivalence of triangulated categories d of x, d of y, preserving the filtration, then x is isomorphic to y. Okay, so it is, at least with this analogy between viewing the derived category as an integral structure plus the Hodge filtration, then you have isomorphism.
And the equivalence of triangulated categories is supposed to be K-linear, or?
Yes.
Otherwise you could twist by an automorphism of K.
Yes. Let's put, thank you.
And it is just triangulated categories in the old sense, not in the any infinity. There is
no infinity. No. Just derived category of coherent sheaves.
So what about the previous question, the map from the isomorphism of x to y to the equivalence of...
So this I don't know the answer to. This is a very interesting question, which is, I'll sketch the argument because it involves, deformation theory and sort of a lot of the classical tools of the deformation theory of K3 surfaces, but the proof does not in any way tell how the isomorphism you produce is related to the equivalence.
Could you remind us what's known for surfaces of other kinds? Because there's a whole class of surfaces where isomorphism of right category applies to isomorphism.
So if either the canonical sheaf is ample or anti-ample, then you know it already. So then you don't need the filtration. Okay, so what's interesting here, maybe I'll put it here, remark is that, and I'll explain exactly what the examples are, d of x equivalent to d of y is not enough. Okay, so this is sort of very classical Mukai, Orlov, many people. Okay, so you can't just ask for equivalence of triangulated categories. This is not enough to imply that x and y are isomorphic. But actually this result, as I'll explain, will tell you exactly to what extent that fails. Okay.
Do you need to assume that Y is a K3 surface?
No, that follows from having the equivalence of triangulated categories. Yeah. So let me review. There's sort of two ingredients that came up in Francois' talk, but let me review just a few basics. So Fourier-Mukai transforms. So that's right. So x, y are smooth projective over K. If I have an object of the derived category of the product, I get such a functor by sending K to RP2 lower star. P. Okay, so that's sort of the standard transform, pull back tensor and push down. And a theorem of Orlov, which is really the sort of key thing to get things off the ground, is that if I have an equivalence is an equivalence of triangulated categories of K-linear, then F is of this form, phi p, for some p. Okay, so this tells you not only, well, it gives you some geometry, it also tells you the candidates, I mean, how you produce, as came up in Francois' talk. What you do is I mean, how could you have a complex on the product? The most natural thing is to take Y to be a moduli space of sheaves on X, and then P to be the universal family.
And dx is dB coherent? Or?
Yes. All the derived categories will be the derived categories of coherent sheaves on smooth projective varieties, so there's no issue about finite. I mean, they're regular. Yeah, bounded. Yeah. Okay, so what are exactly the moduli spaces? Yeah, so I want to actually write down, so X over K is a K3 surface. And so then let me fix normalization. So for a complex, you have the Mukai vector, which is the Chern character times the Todd class of X square root. Okay, and I view this as being an element of and for K3, it's defined integrally. In general, you would have to put some denominators, but for K3, it's there. And it just, I mean, it has a very simple description. It's the rank C1 of E, and then the rank plus C1 of E squared over 2 minus C2 of E. Okay, that's the formula. And let me also fix a polarization on X, so an ample class. And then you can consider the stack of so Giesinger semi-stable sheaves on X with Mukai vector, this vector, are given. Okay, so you fix your nu, and then you make these moduli spaces. So for good V, as Francois mentioned. What do you have? We have A, every semi-stable sheaf is stable, which means that this thing here is a GM gerb over some algebraic space, and in fact is a trivial GM gerb over a K3 surface, which I'll denote in Roman font, like that. And so, I mean, where the universal sheaf lives on the product of X with a stack, but since it's a trivial gerb, you can descend the universal sheaf to, so I'll put universal sheaf E on X cross. So now you have two K3 surfaces and a sheaf on it, induces an equivalence phi E d of X d of NHV. Okay. So this gives a supply of Fourier-Mukai partners for a K3 surface. Let's see. Oh, there's another board. So let me state a theorem, which is that every Fourier-Mukai partner, or meaning K3 surface with equivalent derived category of X, is of this form.
Does it mean that the equivalence is up to isomorphism given by the universal sheaf, or that there is another equivalence?
Another equivalence, yeah. So I'll explain actually how this follows from the other theorem, which where already that ambiguity is present, right? So I'm not saying anything about. I don't know how to relate the equivalence to. I don't know how to lift the equivalence on the derived category to an isomorphism. Yeah. Yeah. In either case. Okay.
So when you say of this form, you mean for some E in the corresponding V, is that it?
Let me put it here, is a MHV for some V and H. Okay. Yeah. So I should say over C, this is somehow classical. Let's see, there are many names here I should put there. But I want to sketch in the spirit of these -2 curves how I view this in relation to the filtered result. Okay. So that's by the following proposition. So let's suppose I have two K3 surfaces. And phi from d of x to d of y, an equivalence of triangulated categories, of derived categories. Then there exists choice, then there exists MHV and sorry, let me say it the way it's written here. Then after precomposing phi with an autoequivalence of d of x and an equivalence d mhv of x, so arising in that way, you can arrange for the equivalence to be filtered. Okay, so you start out with something which is not a filtered equivalence, but then you have these basic steps you can do. You can apply the autoequivalence of d of x, and you can do this game of replacing x by a moduli space of sheaves. Okay, and so once you do that, then you can make, and this is just playing games with the sort of invariance of on the Chow groups, and so then the corollary is this result, right? So that implies this theorem here, right? So once you have the result that two filtered, if you have a filtered equivalence, then they're isomorphic, then from this proposition you get that every Fourier-Mukai partner is a moduli space of sheaves.
And this MHV sits on the x side, right?
Yeah, I mean, I could do it on the other side too, but I have to, yeah. I want y to be MH of v, so I precompose to make it filtered. Okay. All right, so let me state another theorem, which is more subtle, and which is there are only finitely many for given x. There are only finitely many Fourier-Mukai partners. And two, if x is supersingular, so for a positive characteristic, then no non-trivial Fourier-Mukai partners. Okay, so even though I think this condition about preserving the codimension filtration looks very strong, in the case of K3 surfaces, you can recover what's known about Fourier-Mukai partners of K3 surfaces from that one sort of Torelli theorem. Okay. Let's see. All right, good. Okay, so I want to discuss the idea of the proofs. And slash deformation theory of K3s and K3s with the Fourier-Mukai transforms and so on. Let me give sort of the idea over C. I think it's the filtered derived equivalence gives an isomorphism. follows very easily from the classical Torelli theorem. So why is that? The point is that if you have x and y, then you get this phi p, which is given by pullback, tensor, and push down. So that passes to any cohomology theory. And so phi p induces an isomorphism on this, what French Swak denoted H tilde, and I think my normalization is slightly different than his. I think if I change it now, I'll get confused, so let me put it. I think you had a shift by 1. Yeah. Okay, so you do this Mukai lattice, so H tilde, so this is, sorry, my board work is not good. So I define it in this way. So you get an isomorphism on these Mukai lattices, and the filtered condition tells you that it induces an isomorphism on H2. Right? So filtered implies you get an isomorphism on H2, preserving the Hodge filtration. The Hodge filtration. And so we're done by the usual Torelli. Okay, so in some sense, this is a much stronger, we're imposing a much stronger condition than the usual Torelli condition. Let me just remark over here, I should have said this before. In this case, so if you think about it, if I have a point here, let's say K of Z, I look at the skyscraper sheaf of a point Z in this moduli space, the corresponding sheaf over here is the sheaf corresponding to the point Z. So the ranks in general get messed up, right? So here, when you have this kind of equivalence, it's not going to preserve the filtration. I should have remarked that. But once you do, so in general, these things get scrambled up. But once you preserve the filtration, then you're in the usual Torelli theorem setting. Okay, so what do you do in characteristic P? So now we're in a bit of a delicate deformation theory problem of K3 surfaces. We want to think about so how to deform X, Y, and P. The triple consisting of two K3 surfaces, an object in the derived category, and the product. And so how do you do that? You consider this very sort of strange stack, which is the stack of perfect complexes on X cross Y. On X, which are simple. And I'll put it universally gluable. Right, so what this P is some object of the derived category. So simple means that the automorphism functor is just GM. So it looks like a simple sheaf. And this universally gluable means that the negative X sort of functors, P is 0 for I less than 0. Okay, so you impose some condition, and if you impose these conditions, then this is an old paper of Lieblich, which is that this is an algebraic stack. so you have some geometric object to work with. Because it's big and non-separated and all that kind of thing. But, well, in general, if you don't put the simple condition, but the simple condition actually gives us a reasonable space here. So the simple condition implies that you have that this thing dx is a GM gerb over an algebraic space which maybe I'll Roman font dx. So you get the follow. So given a Fourier-Mukai equivalence P, so we put phi P from d of x to d of y. So you have this P in the product. You can view it sort of asymmetrically as being, if you think about y here, and then here's x cross y, you can view it as a family of complexes on x parameterized by y. So here's P. So if you look at a point, you have to verify things like, you basically have to compute xi of py, py. Right, so for these conditions, you have to x0 and the negative x. And this is happening in the derived category of x. But because this is a Fourier-Mukai equivalence, this is the same as xi d of y k of y, k of y. Okay, so you compute the, you can bring it to the triangulated category on the other side. Okay, so these conditions are actually easy to verify when you have a Fourier-Mukai equivalence. And so what you end up with is a map from y to the stack, which is this mu given, let's say mu p. Okay. So it gives you this map, and let me call this mu p bar. And the condition that phi p is an equivalence, actually is fully faithful. Let me put it this way. It's fully faithful. Is equivalent to this mu p bar is an open immersion. Okay, so you somehow translate the condition to have a Fourier-Mukai equivalence to sort of a map from this thing to this algebraic space. Okay, so all right, so what can you do with this? So let me state a proposition. Well, let's consider now the deformation functor of x. So we have a K3 surface. We have its deformation functor, which we know everything about. So A goes to the liftings of...
dx isn't separated, is that the point?
Which one?
dx is not separated?
The Roman font? Yeah, nothing is separated. I mean, I'm not saying anything about global geometry. Yeah. Liftings of x to a. Okay, so we have the deformation functor of x, and I'll put it over here. Proposition. There's an isomorphism. There's an isomorphism of functors. I mean, these are pro-representable, so say it like this, of deformation functors, so that's not such a big deal, but such that for every L in the Picard group of X, so I'd say X and Y are K3 surfaces, K3, and I have a Fourier-Mukai equivalence dx to dy. Sorry, you're right. And let me further assume, okay, sorry, I'm getting ahead of myself. Okay, sorry, thank you. So when you're in this situation, so you can, after changing your choice, changing the choice of P, so you always have to do these kind of basic operations, can arrange that 5P100 is 100, and so I'm assuming this is filtered also. Sorry. So I'm putting a lot of conditions, but once you have that, you can arrange that, and that it takes the ample cone of X to the plus or minus of the ample cone of Y. So now you see why there's really not much control over. You start with some general equivalence, make it filtered, and then you do more operations to make further. So there's not much control. But once you do this, the proposition is that
Does this involve some sort of reflections?
yeah, reflection. It's sort of like I view it by very rough analogy with the classical theory as making reflections and things like that. Yeah. So then you have an isomorphism of deformation functors delta from the deformation functor of X to the deformation functor of Y, such that for every L in the Picard group, so we're looking at K3, so the deformation functor of X with a line bundle is a subfunctor, and so you can ask what it does. So delta of this deformations of the pair XL maps isomorphically to the deformations of the pair Y 5L. Okay, so and because of the way I set it up, this is the class of a line bundle. Okay, so in other words, you can use the Fourier-Mukai transform to identify the deformation spaces in a way that matches up the line bundles. So I'll explain. Yeah. Maybe I should say there's the basic problem we encounter, which I think I'll have time to mention. In the supersingular case, you run into so here, so in the classical literature, like in your papers, you consider deformations of X and an L, but you could also consider deformations of X with a bunch of line bundles. And that gets more and more complicated the more line bundles you consider. But this is an important problem, I think, because there's a number of situations where you might try to deform, if you have a high rank K3, you might want to deform the K3 plus, well, of course, if it's supersingular, you can't deform the whole lattice, or whole neuron severity, but you might want a big lattice. Okay, big Picard of the generic fiber. Okay. Right, so how's this going to work? So the construction of delta. Yeah, so, well, I think it's basically this picture. So you take let's say I have A is an Artinian local W algebra, and I have XA over A. All right, so then I get a lifting of the dx and the dy. So I get, let me do it on, I get dxa, and then here I have the dx that I started with. And then here's my y, which maps here. This is the mu p bar, and this is open. Right? And so, well, open subsets lift uniquely. Okay, and this is open. So there it is. That's the deformation. Okay, so this defines delta.
You know the y is dancing dx?
No. It doesn't matter. I have an open subset and I have a nilpotent thickening of dx could be as bad as you want. Yeah.
It is nice in the sense that it is locally of finite type.
Sure. Yeah.
Or the stuff over A is essentially flat over A.
Yeah. So there's a subtle point which is special to the K3, which is that I need to know this is flat over A. Yeah. Locally of finite type and so on. Yeah, that's right. Yeah, I'm sweeping a lot under the rug, but the main subtle point is, I mean, why couldn't this just be dx? Right? Maybe it was, you need the flatness of this over here.
Generally, it doesn't satisfy any separation.
No, I don't believe so, no.
Well, there are several algebraic spaces. Certainly it is quasi-separated.
Yes.
But not locally separated or not.
I'd have to sit down and think about it, but yeah. But I mean, it's an important point that it doesn't actually, I mean, you have to verify that it has some reasonable properties, but not, it doesn't have to be a projective variety or anything. You're lifting open subsets. Okay. Now, in fact, there's a little bit more here, which is you can lift the p. So you see there's an annoying thing, which is that the Roman font dx is something like a coarse moduli space, and you really want to lift the Fourier-Mukai transform too. So in fact, this takes a little more work. Can lift the p, which is really I mean, this is this map mu p to pa over in d of xa cross over a with y. Okay, so this takes some more work, but let me not dwell on that. Okay, and so now how do you proceed? You use this here, because we want to lift a characteristic 0. You better preserve some ample line bundle so you can algebraize and get the whole thing. So now, so what do you get? You get a let's say a mixed characteristic DDR V, and deformations x, y, p over v, lifting x, y, p. And then
because you know the def x over L is flat over W. Using it.
Yeah, I know. Yes, absolutely. So I have at least one map to a mixed characteristic DVR, right? So and that'll, I'll mention a related point. Right, and so then generic fibers. And actually, I mean, there's a lot to check, but this deformation here. Actually, if I start out with a filtered equivalence satisfying those conditions, this deformation is also going to be a filtered equivalence, okay?
Is it unique? Is it PA unique? Is it unique, the PA or the script P or whatever?
This thing here? Let's see, so I have to calculate. No, I don't need it to be unique. Yeah, I mean it has to do with this this sort of gerb there, and whether there could be a cohomological, I mean a torsor that.
So how do you get this V?
Well, okay, so so what do? I choose my an ample line bundle on X, and then I look at the deformation space of XL, and then it gets paired up here, and then the only thing I have not sort of discussed is why you actually get an actual P, because you only have a map to the Roman font. Right, so I have a map to the coarse moduli space. I have to trivialize a gerb over that to get the actual P. Okay. All right. So then generic fibers admit a filtered Fourier-Mackay equivalence, and so then you have to replace V by another extension to get the generic fibers isomorphic, and then you go back down because using some minimality of K3 surfaces. Okay, and then use characteristic zero result, and then go back to closed fiber. Okay, so there's a lot of technical points here, but I think the key idea is this kind of. Sorry, yeah, I should make complete DVR. So
the fact that lithium preserves the filtration is automatic in this case. It's not nothing you have to impose.
No, it's not something. Yeah, it just follows from the. It comes from this sort of big stack here. But yeah. Okay. All right. So let me make a remark. So that gives. That if you have a filtered equivalence and they're isomorphic, the finiteness result, how do you get the finiteness result and the, I think the supersingular case is maybe the most interesting because how could you prove that, in fact, that if you have a supersingular K3, then any Fourier-Mackay partner has to be itself. This argument that I just sketched does not lend itself very well to that, but the problem you encounter, so for a supersingular K3, so sort of people who do lattice theory know that if you have a Néron severity which has rank at least 3 in characteristic 0, then you don't have non-trivial Fourier-Mackay partners. Okay, so now the game becomes deform K3 surface plus a rank 3 subgroup E inside Néron severity of X, and there's a lot to do, but that's the basic deformation theory problem you encounter. And so so in this case you can calculate using the deformation theory of polarized K3s that you do still have a characteristic 0 point of the deformation space, but maybe I'll put it as a question in general. I don't know in general. I don't know how to describe deformations, let me write this way, deformations of XE. So where you fix the groups. On Arthur's paper, there's discussion of if you have a, you can get a quadratic thing, make a quadratic extension, and in Deline's article and so on. But in general, what does the deformation space of something like that look like? I don't know. All right. It might not have any characteristic 0 points. Yeah. For a super, take the supersingular case. Yeah.
When you look at this thing about this P and PA, so there was a GM gerb there, and when you have this the Artinian local ring deformation, it could be that you're talking about characteristic piecing. So it could be that you don't know that the H2 class is 0 over an Artinian.
So the point is that you do some trick with the determinant, of the P and relate that to the obstruction class. So there is a serious argument there. I mean, it's not, but you have to do, you're right, there is an obstruction in general, but if you calculate what that obstruction is, you can relate it to the determinant of P. And so if you do it, if you set it up right, you can arrange for that obstruction to vanish.
The determinant of the, okay.
I mean, you can, because it's a one-dimensional obstruction space, and you have to relate what that obstruction is to something having to do with P. Yeah. So it's a non-trivial point. Yeah. Okay. Let's see. Yeah. 2 or 3 minutes. Okay. So maybe I'll just mention sort of a couple more questions here. So I don't know how to do this in general. The other point is, which was raised several times, is the way this is set up. This, you know, the isomorphism. Construct the isomorphism, right? I mean, from d of x. Right, so I don't know how to just take the derived equivalence and then construct the map, right? This seems, I don't know where to do it. It's tempting to think about the Chow group of 0 cycles, and sort of, if it's filtered, you get a map on 0 cycles, but that sort of looks like you should just see the morphism, but I don't know how to do that. Yeah. And I guess the other question, I won't write it, is I don't know in general whether filtered equivalence is a much stronger condition. A derived equivalence is much stronger than sort of classical Torelli. There seems to be promising progress in the hypersurface case, but I think that's about where we're at right now. Thank you.
So is that problem the problem in generalizing to non-algebraically closed space theory?
No, the problem is that sort of the way I've presented, the way I understand it, I don't know. I mean, in the honest Torelli situation, you know a lot about the isomorphism in relationship to what you do in cohomology, right? So you have some transformations that you understand, and then you can lift it to an isomorphism if it takes the Kähler class to the Kähler class and so on. So, but here I think it's a total mess. What is the relationship between the isomorphism and the equivalence of triangular categories? I don't know.
Which isomorphisms correspond given specifically by morphism?
Right. Yeah. So given you take this thing, how could you even maybe you could impose some condition that says then there's an actual map. Right, that gives it, I don't know.
Very nice question. So we discussed the supersingular case.
Yes.
So the object you have the ordinary case.
Yeah.
And then formal modular now group structure, formal torus.
Yes.
So then what is how does deformation theory work? I don't see it because either it's local or global. I'm not so sure.
Could you repeat the question?
Well, what is the story for ordinary?
Well, I guess in the ordinary case we know dx is really clear. From def x, not dx, but def x.
Oh, def x, yeah, def x, yes. Yeah, so what happens under this delta? Well,
and what is the story then?
Yeah, I don't know because I don't understand sort of the general phi p. Right, so I mean somehow
the basic ingredient was the tangent space to Roman dx. It was x1.
That's right. Yeah.
So that was basic ingredient to get your.
Yeah. So then I have to see what these Chern classes do as it moves over to the other side.
Yes. The ordinary case I'm interested in. Yes.
I see. Actually, Francois suggested, and I think this is another promising, it may work, to prove it using Arthur's theorem on deformed to the supersingular K3s.
Any more questions? here.